We assume that basically there is the noise added here in the market random walk is Gaussian, and we don't know the direction. But if you look at the markets at different intervals, then we tend to see non-Gaussianity and the asymmetry. So in this case, for instance, if you look at the histogram of daily returns, so in this case, basically the x-axis is the return. So in this case, for the first plot, it's the daily return. So we look into the S&P 500 market, we take its daily returns and plot its probability distribution function, how the density of the returns looks like. And in this case, this kind of looks like a Gaussian distribution. So if you look at the daily frequency, then this is quite similar to Gaussian distribution. So for daily assumption, we tend to say that the random walk assumption, the time series that we observed, if the t is day, then if t plus 1 is the next day, then it's kind of satisfied. But we also look at different intervals. So for instance, here we look at the weekly one, and again, we look at the bi-weekly one, monthly one, bi-monthly one, and the quarterly one. So in this case, again, if you look into the weekly log returns, it's again looks like a Gaussian, even though there is some basically asymmetry and there is some non-Gaussianality as well. There are some heavy tailness more than Gaussianality. Then it's still Gaussian. It's still kind of Gaussian. And again, if we try to look at the biweekly, again, slight asymmetry. So because the returns will not be on this zero and it's not symmetric, so there's a slight skewness towards the right side. So there tend to be more positive returns than more negative returns when you look into the biweekly domain. And in this case, another thing is you tend to see that basically tails kind of increases. So this is more tails than Gaussian. So that's why the Gaussian assumption tends to fall apart, more tails than Gaussian. And another example here is monthly log returns. So if you look at the monthly log returns, again, this becomes more and more skewed when you look at the larger intervals. So the longer interval you look, longer interval look, more non-Gaussian it becomes. More non-Gaussian it becomes. And similar things can be said for the remaining two plots. In the remaining two plots, we have this histogram of bi-monthly log returns, and as well as quarterly log returns. And again, both of them, especially if you look at the quarterly one, then this is not Gaussian. So definitely there's a skew towards the more positive side. So which means that the market is not Gaussian. So there's a trend. So we can think that the markets will basically be more positive than negative. So if you want to bet on the market, so this is not Gaussian. And again, there are more tails if you look into the side. So there are heavy tails on the negative side than tails compared to basically the positive side. So if we look into the asymmetry, so again, if you look at the skewness of the log returns versus the frequency, then basically we tend to see that the frequent it becomes, the skewness kind of basically decreases, meaning that it becomes more and more skew. So if there is basically the skewness is, as you remember, defined as the third moment. So it's basically the skewness is defined mu square, mean cube, defined by the basically standard deviations cube. So in some cases, then there are some different definitions as well. But in general, it's the third moment. Skewness is third moment. So first moment was mean, second moment was variance. And in this case, the third moment is basically the skewness, which is related to asymmetry. And in this case, if the frequency of the data increases, or if we look into basically the returns in terms of the certain frequencies, then basically data becomes more and more skew, as we see in this plot. And another thing is we can also look into the heavy tailness. So in heavy tailness, we have this basically QQ plots, quantile plots, to understand the heavy tailness of S&P 500 log returns. So in S&P 500 log returns, we have this theoretical quantile on the x-axis, so which is basically theoretical quantile here, and from 0, -1, -2. And in this case, this corresponds to the sample quantile here. And basically, the more heavy-tailed it becomes, the different it will becomes from this kind of function. So for basically the functions that you see here or in the middle, the quantiles perfect matches. But for other quantiles, so these are the cases that are basically that shows the tailness. So the more that it deviates from this curved shape, then these are the ones that we tend to see the heavy tailness. So these are the heavy tails. Again, if we look into basically increase the frequency, and if you look at the weekly, bi-weekly, monthly, bi-monthly, and quarterly one, we tend to see more skewness. So for instance, in bi-weekly one, so these are the heavy tails. So since this shape deviates from what's expected from the theoretical quantiles, then we tend to see more heavy tails. And this tend to see the deviation from basically the Gaussianity. So again, if it was uniform, then we tend to see this line. So this line here is basically the tailness for the uniform distribution, where there shouldn't be any tailness, so it should be completely uniform. But for Gaussianity, we tend to see something like this. And the more there are points that deviates from this heavy tailness, and we basically, by saying this, we can tell that the frequency, if the frequency increases, the basically distribution becomes less heavy-tailed. And again, there are certain tests to assess, which we not go in detail, but assess whether this S&P 500 is basically is heavy-tailed or not, and they will be based on the QQ plot. And again, if you notice here, for instance, this is quite skewed. So for instance, more side from the 0, this side is smaller than the side on the positive side, which looks like a uniform. And then there are heavy tails and tails that are heavier than expected by the Gaussian distribution. So these are the ones, again, for the heavy tailness. And again, the heavy tailness is defined by the Ford moment. So it's defined by the Ford moment, and which is also known as kurtosis, which defines the heavy tailness, and it's the fourth power of the mean divided by standard deviation's fourth power. Again, there are certain definitions. Some of them subtract 3, some of them subtract 4, and there are certain definitions. But again, if we subtract here 3 and then take the fourth power, then basically this becomes the excess kurtosis. And in excess kurtosis, basically, if you look into the plots, what we need to know is basically for different frequencies, there is no single increasing or decreasing trend. So the kurtosis kind of decreases and becomes more and more heavy tailness when we increase the frequency, even though it's kind of, if you look at it, there is no single trend, but there are certain fluctuations over time. And again, so aggregational Gaussianity is a behavior that we tend to see in this plot. So again, if you look at the QQ plots, where it plots the theoretical and sample quantiles for daily, weekly, bi-weekly, monthly, bi-monthly, and quarterly standards log returns. So again, these are the standardized log returns where we remove the impact of the volatility clustering. We still tend to see some heavy tailness. So in this case, basically, again, we tend to see heavy tailness, but this is more apparent in the standard data on the daily case compared to the quarterly case. So for instance, if you look into the plot on the daily standardized log returns, then we tend to see asymmetry and basically conditional heaviness in the here and in this region as well. So that's why it's kind of not same as Gaussianality. But if we look at the returns that are in a longer period, such as, for instance, bi-monthly returns, then the basically theoretical and sample quantiles almost matches with each other. And meaning that this becomes almost Gaussian distribution. And the reason here is that by central limit theorem, so even though the individual distributions or the individual returns are not Gaussian, when we add them up in the log domain, we are basically adding them up, then the resulting distributions tend to become Gaussian. And we see in these plots the impact of this central limit theorem, and basically in the standardized log returns. So if we increase the interval that we are looking, such as monthly, bi-monthly, and quarterly, for instance, then basically the distribution becomes Gaussian, especially in the bi-monthly case, as you noticed here. And this is known as aggregational Gaussianality, or basically this is one term, or conditional heavy tailness is another term, is added, named to this event.